Hi, in this video I will go step by step and explain the concept of fully homomorphic encryption. I will skip the complex math and focus on the core concepts that are necessary to understand this groundbreaking technology. And by the end of this video, you will learn first, what problem it solves, second, how it works technically, third, why is it becoming a trending topic nowadays, with many real-world applications and tool support from companies like Microsoft and Google, and finally, what the future holds for a fully private internet. So let's dive in. Let me begin with introducing the main problem. If you are watching this video, you are probably interested in cryptography. Cryptography is about using mathematical equations to transform secrets so that trust can exist without trust. But that's actually not that easy, and anyone who has really deep dive into encryption systems can tell you that. Here is what a ChatGPT session looks like right now. You send a question or a prompt to OpenAI in plain text or by voice or whatever, but in the end it is converted into plain text, and then OpenAI models process your questions and give back a response to you in some human understandable format, like for example in plain text as well. Do you see the problem here? You are sending and sharing your thoughts, your information, your personal feelings with OpenAI, and this is probably not what you want. What you want is the output of the processing engine, the answer, but you don't want OpenAI or any AI to know about your question. So let's go back to the basics. All forms of data can only exist in one of three states. At rest, that means it's stored on disk in a database, for example. In transit, that is moving over a network, like sending a message on your phone or making a comment on a YouTube video. And by the way, leave me a comment down below to put some data in transit. And number three, in use. That means being processed in memory. For example, when an AI model is executed to produce an output. And here's the thing. Today, we have robust solution to encrypt the data for the first two states. But in use, when data is loaded into RAM and processed by CPUs or GPUs, then it is decrypted. And this is the Achilles heel of modern security. Cloud providers, insiders, attackers, or compromised CPUs can read your plain text data. If you think about every major data breach you have heard of, for example, the 2014 celebrity photo leak in the Apple Cloud, or the Capital One hack, or the 23andMe genetic data theft, they were all failures of encryption when data was in use or at rest. The moment data gets loaded into memory for processing, if it is not properly encrypted, then it becomes vulnerable. Imagine you buy something from an unknown online shop. Your credit card number is encrypted during transmission, but the website still stores your number without encryption in its database. A hacker that breaks into the website could get your card stolen anyways. And this actually happened as shown in the example before. So the key takeaway here is that encryption is necessary but not sufficient. Securing only the path is meaningless if the endpoint is vulnerable. You can think of it like using an armored car to deliver cash, but leaving the bags of cash on an open park bench at the destination. What is the solution then? Well, imagine if the data could stay encrypted through its entire life cycle, which we can call full privacy computing. Fully homomorphic encryption aims to make this possible by making both the transit and the endpoints secure. But before diving into it, let me do a quick recap of the very basics of cryptography. As you may already know, cryptography systems rely on hard problems. And by hard problems, I mean those with no known polynomial time solutions, or what in computer science is known as NP hard problems. To be useful, these problems must be easy to compute in one direction, but extremely hard to reverse. Such problems are called one-way functions, and all cryptography depends on them. A classical example is multiplying two large prime numbers. It is fast once you know the numbers. However, if you only have the result of the multiplication, then it is painfully slow for modern computers to find out which prime numbers produced that result. Think of it as when you take a piece of paper and shred it. Doing that is easy, fast, and effortless, but doing it in the other way around, I mean reconstructing the original document from thousands of tiny shreds, is practically impossible. But the question is, how to make the data in transit, in storage, and in use secure? Coming back to the ChatGPT example given before, you could encrypt your question. The server then runs the model on the encrypted data, sends back an encrypted answer, and only then you can decrypt it. So let me go step by step. First, you create a key pair, a public key and a private key. You log your message with the private key. You send the encrypted prompt and your public key to OpenAI server. This way, they can never decrypt and see your prompt. So all that the server receives is your ciphertext and public key. And then, assuming it has a model that can operate on the encrypted text tied to your public key, I mean computing without knowing, then the server computes on the ciphertext and produces a ciphered answer and returns the still encrypted results to you. And back on your side, you unlock the answer with your private key, which the server never had. So in summary, the model will run over encrypted data inputs without ever decrypting them. So the question is, what kind of technology can make this possible? And here is where fully homomorphic encryption comes in. The term homomorphic comes from the Greek homo, meaning same, plus morph, meaning form. It means having a structure preserving map between two algebraic structures. Fully homomorphic encryption is homomorphic because operations on encrypted data can be mapped onto those on the original data. The homomorphism in category theory is often shown by a commutative diagram, where you can go from a point to another by interchanging the order of operation, like in this diagram. For fully homomorphic encryption, you can go from A, B to EA multiplied by B in two separated ways. In other words, you can multiply while things stay encrypted, and you will get the same answer as if you had unencrypted them first. So homomorphic encryptions make the diagram commute. Whether you compute the encrypt or decrypt and then compute, you arrive at the same encrypted results. Let's look at an equivalent diagram for a client-server perspective. As a simple example, imagine that you have a set of emails and you want to use a third-party spam filter to check whether or not they are spam. The spam filter has a desire for privacy of its algorithm. Either the spam filter provider wants to keep their source code closed, or the spam filter depends on a very large database that they do not want to reveal publicly, as that would make attacking easier, or both. However, you care about the privacy of your data and don't want to allow your unencrypted emails to a third party. So here is how you do it. You encrypt your email, then the server executes a function that detects spam on encrypted data and sends the output to you, which then you can decrypt and map to the unencrypted emails to remove them. Another helpful analogy to fully homomorphic encryption is the Fourier transform, which converts a signal from the time domain into the frequency domain. Computations performed in the frequency domain are equivalent to those in the time domain and vice versa, meaning that you can compute in either domain and still get the same result. In a similar way, fully homomorphic encryption operates between plaintext and ciphertext domains. Transformations done in the plaintext domain are equivalent to those in the cipher domain, and vice versa. And to do this transformation, fully homomorphic encryption uses lattice-based cryptography. Imagine a multidimensional grid of points extending infinitely in all directions. At the heart of lattice-based cryptography are problems that are believed to be extremely hard to solve even for quantum computers. Two of the most well-known examples are shortest vector problem, or SVP, which is about finding the shortest path between lattice points. And another one is the closest vector problem, or CVP, which is about finding the lattice point nearest to any given point. And hacking these systems becomes extremely hard, so much so that it is believed that even quantum computers can crack them efficiently. And this makes fully homomorphic encryption inherently quantum resistant, which is a very important property to prepare for the possible quantum computer future. Lattice-based fully homomorphic encryption schemes rely on the learning with errors kind of problem. At a high level, this kind of problem looks like this. You have a known matrix A, S is a secret vector or key, and E is a random small noise. Then you calculate B, which is equal to A multiplied by S plus E. I mean, B is a noise linear combination. And then you generate the public key A, B. Notice that A multiplied by S is linear, so visually forms a lattice. In other words, A multiplied by S is on the lattice point, and the addition of noise E makes the resulting A multiplied by S plus E equal B drift from the lattice point. Also, note that the noise is sampled from a narrow random distribution, so that B doesn't drift too much from the lattice point and is closer to another lattice point. So the problem becomes this: if an attacker wants to find the secret key S from the public key A, B, she needs to solve the problem of finding the closest lattice point equal to the closest vector problem, or CVP. And the closest vector problem is believed to be NP-hard and even quantum resistant. So to sum up, this type of encryption works because of noise, and encryptions remain secure because decoding a lattice point with noise is very, very hard. And all of this, of course, is not new. In the past decades, we have experienced what is known as the Moore's law of fully homomorphic encryption. There has been 4 generations of software enhancement. In the first generation, in 2011, the implementation of fully homomorphic encryption, bootstrapping, on an IBM took around 30 minutes per bit. However, by the third generation in 2014, the bootstrapping took milliseconds. Now we are at the fourth generation, and with approximate floats, this technology is enabled to work on machine learning or even AI applications without no problem. So since 2011, fully homomorphic encryption performance has improved 8x every single year, and recent discoveries are accelerating the timeline. A recent paper published in June 2025 claims 1000x higher multiplication throughput and 10x lower latency for large integer operations. Alongside algorithm improvements, hardware improvements are also happening, which compounds the effect. And hardware acceleration could increase the speed by more than another 1000x or something. So we are quickly getting into a point where many of the applications of homomorphic encryption in privacy-preserving computation are starting to become practical. Additionally, research into the more advanced applications of lattice-based cryptography used in homomorphic encryption is rapidly progressing. So this is a space where some of the things can already be done today. We can hopefully look forward to much more becoming possible over the next decade. Homomorphic encryption is already being applied in real-world applications. For example, in Apple's privacy feature for private information retrieval, which is called live caller ID lookup. And another example is also for doing machine learning on encrypted data done by Apple for private nearest neighbor search. Another example is Microsoft Security for password checkup in the Edge browser. They do private set intersection on encrypted data. I personally know about two well-established open source tools to do fully homomorphic encryption. The first one is Microsoft Seal, which is an easy-to-use and well-established homomorphic encryption library developed by the Cryptography and Privacy Research Group at Microsoft. And they are also building Thin Seal on top of Seal, which is a library for doing homomorphic encryption operations, specifically on tensors for machine learning operations. Another one is from Google. I think the tool is called HEIR, which is actually a compiler framework that translates high-level annotation code into optimized fully homomorphic encryption pipelines. So Seal is mature, battle-tested, high performance, and it is often the entry point for many real-world fully homomorphic encryption tasks. And HEIR is more like an universal translator that doesn't commit to any single scheme. Instead, it adapts your code to whatever fully homomorphic encryption engine or hardware you prefer. So, in summary, data breaches are almost unavoidable. The only way to protect data is to keep it always encrypted on servers, without the servers having the ability to decrypt them. This means that data should be encrypted even when computations are performed on it. And fully homomorphic encryption enables computations on encrypted data. Although fully homomorphic encryption is not practical yet for many applications because of its very high computational overhead, it is still practical for some applications. Fully homomorphic encryption algorithms are getting better every year, and the result is that a feasible real-world applications are on the increase. I hope the adoption of fully homomorphic encryption will increase very rapidly, and I hope that it will conquer many more real-world use cases to the point that most cloud computations can be done with it. So I'm going to end this video with a quote from Jean Spafford, who points out that while we focus heavily on protecting data in transit, we often ignore security at the endpoint. He says, using encryption on the internet is the equivalent of arranging an armored car to deliver credit card information from someone living in a cardboard box to someone living on a park bench. And fully homomorphic encryption is very likely to be the future of fully private computing. I hope you enjoyed the video. See you in the next one. Bye.